So first we'll see the solution for the previous problem. What we have taken up, that is design of sleeve and cotter joint. Then we'll move to the next type of cotter joint, that is zip and cotter joint. So here in this problem, it is a design of a sleeve and cotter joint, which is subjected to a load of 60 kilonewtons, and he is given that all the parts of the joint are made of same material, such that the tensile strength is same for all the components, shearing strength is same, as well as crushing or bearing strength also same. The allowable stresses he has given it as 60 MPa, shear stress 70 MPa, and crushing strength is 125 MPa. So this is the data what he has given. The joint is subjected to 60 kilonewtons, and these are the allowable stresses what he mentioned in the problem. Suppose sometimes they may not give these things, so then in that case what you have to do is you have to pick these values from the data book. So that is the point what you need to remember. Always they may or they may not give these values. So since the design data book is allowed for the examination, so we should know how to pick the data from the data book also. So that is also important thing. So sometimes the examiner may want to test that point also, whether you know how to use the data book or not. To test that, they intentionally omit these values and they'll give only the material value and ask you to pick the values from the data book. So in that point, you should be ready to solve that problem. Okay, right. So coming to the design of this joint. So in yesterday's class, we discussed what are the various parameters for this, dimensional parameters for this sleeve and cotter joint. So we have to find out what is D, then D2, D1, T and B, T, B, A, C. So 6 parameters you need to calculate. That is D, D2, D1, B, A, C. We know what are those parameters also. D is nothing but the diameter of the rod end. D1 is the extended portion of the rod end, or diameter of the extended portion of the rod end, or inside diameter of the sleeve. D1 is the outside diameter of the sleeve. B is the mean width of the cotter. A is the distance of from, what is that? I forgot. Yeah, this one. This is distance of slot. This cotter to the sleeve end, and C is distance between the rod end to the start of the cotter hole. So these are the parameters we need to calculate. Once you've done that, then the remaining things. So capital L, small l, all these things are the small l. So these two dimensions, and even for that matter, this total length of the joint, all these things can be picked from the empirical relations. So that is, this dimension is 4.5D, means obviously this total dimension is 90. So okay, so for that first we need to compute what is this value, then we need to compute this value, then this value, and then after that B, then we'll take up A or C. So then it will be over. So for that you should know what are the failure criteria to find the dimensions. And also once you calculated that, you need to check for the crushing stress also, whether the crushing stress is within the given allowable limit or not. You need to verify that also. So now first to find out this D, what you have to do is you need to consider the tensile strength of the rod. So or the tearing strength of the rod. And go to the problem. So here considering the failure of the rod in tension, so your failure equation is applied load, which he has given it as 60 into 10 cube newtons. It should be equal to the tensile strength of that rod. So that is 5 by 4 D square into sigma T. Sigma T is given as 60. So only unknown is D. If you solve that, you will get D is equal to 35.7 mm, or let us say we'll round that one to 36 mm. So that is D is known to us now. In the first step, we need to calculate D, that is nothing but the diameter of the rods. Then we'll move to the next one, that is D2, diameter of enlarged end of the rod and thickness of the cotter also. Here we need to calculate both. just what we do is we'll assume that empirical relation between D2 and T. So this is the equation what we need to consider. So in that your D2 is the diameter of the enlarged end of the rod, or you can say inside diameter of the sleeve. Both are same. So therefore here we'll take a T is D2 by 4. That's what I showed here. E will be taken as D2 by 4. So then if you substitute, given load is 60 kilonewtons, which is nothing but 60 into 10 cube newtons. It should be equal to the tearing strength of the rod across that slot. That is nothing but 5 by 4 D2 square minus D2 into T. If you substitute for T is equal to D2 by 4, so then you will get only one equation in terms of unknown D2 only. So if you solve that, you will get D2 is 43.2 mm. So let us say it is equal to 44 mm. We'll round it up to 44 mm. So once you calculate this D2, then you have to calculate T. T is nothing but D2 by 4, so you will get it as 11 mm. So once you have D2 and T, then you need to check for the crushing strength of cotter as well as this rod. So first we'll calculate the D value. So D is going to be 11 mm. Then we need to check for individual crushing stress in the rod or cotter. So both should be same, because the crushing area is same for both cotter as well as rod. And also as mentioned that all the materials are made of same material, means the crushing stress is allowable crushing stress is also same for both rod and cotter. So if you check for one, then that is sufficient. So now that is nothing but here the load is given as 60 kilonewtons. It should be equal to the bearing area, that is D2 into T multiplied by sigma C, what we want to compute. So that means what is the magnitude of this bearing stress in this, either in the cotter or in the rod. So it comes out as 484 sigma C, which should be equal to your applied load. From that you will get sigma C is 124 MPa or 124 Newton per mm square. But what is the allowable value he has given in the problem data? In the problem he has given it as 125 mm as the allowable bearing stress. Since this individual stress is less than this 125, so then you can say that our D2 and T are within the safe limits. So that means whatever dimensions you calculated, that is for D2 and T, D2 is 44 and T is 11 mm, they are safe, because with these two dimensions D2 and T, the individual crushing stress is less than the allowable stress. So we can say the design is safe. Then the next one is we need to calculate the D1, that is nothing but outside diameter of the sleeve. So you can calculate this outside diameter of the sleeve just by considering the tearing failure across the slot. Tearing failure of the sleeve across the slot you need to consider. So for that, this is the resisting area for the tearing of the sleeve across the slot, and then multiplied by the tensile strength. So which is sigma T will give you the total shearing strength of the shearing strength of the sleeve across the slot. It should be equal to your applied load, that is 60 kilonewtons. So in this equation we know everything except D1. So you substitute those values here, and if you simplify this, you will get a quadratic equation for D1. Even in case of the spy-guard joint also, socketed spy-guard joint also, we got something like this only. So for always for D1, you will get a quadratic equation only. So then if you solve this, so you will get, of course, since it is a quadratic equation, there will be two roots for the quadratic equation. So generally you will get one is positive, other one is negative here. So we will ignore the negative root because we don't have any negative dimensions. So always you have to consider the positive value only. So if you take positive root, it comes out as 58.4 mm. So then let us say we'll round it up to 60 mm. So that means now we calculated the three dimensions D1, D2, D. So then we need to compute what is B, that is mean width of the cotter. That mean width of the cotter is calculated based on the steering strength of the cotter. We know the cotter is in double shear, therefore this is going to be the shearing strength of the cotter. 2 times B into T into tau is going to be the shearing strength of the cotter. So it should be equal to the applied load, that is 60 kilonewtons. So from this equation you will get B as 38.96 mm So let us say it may be rounded up to 40 mm. Then once you have done that, then the remaining two dimensions, that is A and C, you need to calculate. So here in any order you can calculate A first, C next, or C first, A next. Like that also you can do it. It doesn't matter here. So but only thing is without D2 and D1 you cannot calculate these dimensions. So that means first you have to calculate D1 and D2. Then only you can go for A and C. Without D2 and D1 you cannot do this. Even the C also. Without D1, C involves you require both D1 and D2, whereas A involves you require D2. So that means first you have to calculate D1 and D2, then only you can come for these A and C values. So now if let us say if I consider A, so then that is nothing but you need to consider the shearing for A, you need to consider the shearing failure of sleeve end. So you need to consider that. So if you consider that, again here it is in double shear. So the area of shear is nothing but 2 into A into D2 multiplied by tau. It should be equal to the applied load. From that, if you solve that equation, you will get A is equal to around 9.74 mm. So then we can round it up to 10 mm. So therefore, your A is 10 mm. Then once you got that, then the final parameter is C. So for this, again you need to consider the shear failure of the sleeve end. So for this, you need to consider shear failure of the rod end. For this, you need to consider shear failure of the sleeve end. So I think here maybe this is something wrong. Here he has taken the parameters as A and C in different way. Okay, let me go back to the diagram what we have taken. So here A is sleeve end, dimensions of sleeve end A, and C is dimension of rod end to the rod end. So C is nothing but dimensions of the rod end. So maybe here he has given it a wrong way. So that's why I had a doubt here. So maybe you make a mistake, you make a correction here. So this is sleeve end, it is not a rod end. So this is sleeve end here. And here it is not sleeve end, here it is a rod end. So
sir, A is equal to 17
A is equal to
17 వస్తుంది సార్. అంటే ఫెయిల్యూర్ ఆఫ్ స్లీవ్ ఎండ్ ఇన్ షియర్ అంటే D2 minus D1 వస్తుంది సార్. 2A into D2 minus D1 into tau వస్తుంది సార్.
Right, okay.
D1
okay.
minus
maybe yeah, formulas are okay, right? But only thing is he has interchanged those parameters then. So what you have to do here is you have to take this dimension as C instead of this one. Here you have to use C. As per the duration, here you have to use C here. Then you have to calculate C here. Then here you have to calculate this one. You have to take this one as A and this one as A. So then C is going to be 10 mm, and with this calculation you will get A is equal to 28 mm. So don't take it.
D1 is equal to 70 sir.
Yes.
D1 70 sir, 60 కాదు sir.
D1 is 70.
Yes sir.
Why? So you calculated properly these things?
Yes sir, D1 అప్పుడు చెక్ చేసాం సార్ నిన్న.
No, here he has given the calculation. See what is the calculation he has given. 5A4 means 0.7854 D1 square minus D2 square. So what is the value of D2 to take? D2 is 44. So 44 square minus D1 minus 44 into 11. So you check this equation whether you are getting this equation or not, or else this equation or not.
వచ్చింది సార్.
For this equation, what are the roots? If you want, you can check it. I think. Okay, so anyway, it is going to be only numerical calculation only. I have taken it straight away from the textbook. I have not verified these values. Just you verify that you do the calculation and check it here. So here how much you are getting? 102 plus 14 means 116 by 2 means it is 58.4 only, na?
Yes sir, correct sir.
Then okay. Okay, right. So it is 60 only. So then if you use the dimensions here, you will get this is 10 mm and this is 28 mm. So once you done this, then in the examination point of view, what you have to do is you need to draw the joint also. If the question comes in the examination, what you have to do is you need to not only calculation of these parameters, you have to draw the joint also to get a full marks. You need to draw the joint neatly, and then you need to show what are those various proportions also, what are various dimensions you calculated. Then only it is completed. Otherwise, simply using data book and calculating these formulas and giving some values is it's not a complete solution. So what you have to do is you need to draw the joint and then you need to show the dimensions also. So for that, if you don't need to remember the joint, so it is already there in the data book. So use data book and take the figure from the data book, and using the data book you can draw the joint and you can represent all these dimensions also. So therefore you need to have a take empirical relations to find out these two, that is capital L and small l. Capital L is nothing but 90, small l is 4D, so that you can take and you can find those dimensions also. So with this, we computed all the parameters which are required for this sleeve and cotter joint. So that is the solution for the given problem. Okay, so this is how, if it is sleeve and cotter joint, it is somewhat easy and compared to socket and spigot joint. In the sleeve, in case of sleeve and cotter joint, the number of parameters are less. So you can easily do this. Only 6 here. There in case of socket and spigot, you have 9 to, I think 9 is there. Right? I think all of you done this. Okay. So then what we'll do is we'll move on to the next type of joint, which is jib and cotter joint. Before going into that, so the one question what we need to answer is why we are using jib in case of these cotter joints. So the reason for this figure will explain you that reason why we need to use that jib and cotter joint here. Suppose, so we know that always the cotter is, for the cotter the width is not constant, it is going to vary from top to bottom. So why we are providing the tapper for the cotter? For easily withdrawal of the cotter from the joint. If you want to disassemble the joint, you need to withdraw the cotter. So for easy withdrawal, we are providing the tapper on the cotter. But okay, so that is the purpose of providing the tapper. But with this, there is some disadvantage because your cotter is having the tapper in this side. So that means here you have a rectangular hole which is created either in the rod or what I can say, rod, you can say rod, in the rod or maybe in the sleeve also, it is a rectangular hole is there, so which is not having any tapper here. So therefore, whenever if your rod is subjected to some tensile force, let us say it is a tensile, it may not be always tensile, it may be compressive force also. Then what happens here, imagine, so because of the clearance here, this cotter will tilt like this. So the cotter will tilted in this direction. So you can see the tilted portion also here. You can see that here. It will try to tilt like this. So because of this tilting, what happens is there is a bending in the cotter. There is a bending in the cotter, and not only cotter, here this part, this connecting part also subjected to some bending parts. So if you say this is a sleeve, this sleeve is also sleeve or socket. This is also subjected to some sort of bending. So here our intention of creating cotter joints is, in case of cotter joint, there should be only axial loading. So we don't want any kind of bending load also. So therefore, to avoid that bending, we need to arrest this tilting of the cotter. Well, even though you are applying an axial load here, so with this axial load will cause the tilting or bending of this cotter. So we don't want that in case of this cotter joint. We don't want bending in the cotter itself. So to avoid or to overcome the bending problem, what we need to do is we need to provide another component which is called jib. The purpose of jib here is we will provide or to eliminate the tilting of this cotter or maybe this sleeve is subjected to a bending stress. To eliminate the bending stress, we need to provide a cotter to the joint. So again, So once you provide a jib to the cotter, then there may be another option also. Next question is how to provide the jib on one side or both sides. So that depends upon, again, depending upon the tapper how you are using. So if your cotter is having tapper on only one side, we need to use only one jib. If your cotter is having tapper on both sides, if you look at this picture here, it has a tapper on both sides. So on both sides you need to provide the jib so that you can arrest or avoid the bending of this cotter. So like that, depending upon the tapper you are using on the cotter on both sides or a single side. So this is what is the advantage of providing cotter on both sides. So here it is going to be symmetric now. So earlier it is not symmetric. If you provide the tapering only on one side, it is not symmetric. So here now it becomes a symmetric here, and then withdrawal of the cotter is much more easier when compared to this one. So because the tapering is there on the both sides here, not on a single side. So this is going to be the most advantageous one when compared to this one. So because you can easily withdraw the cotter from this when compared to these two. Okay, so this is the purpose of providing the jib in the cotter joint. So one is the main reason is to avoid the tilting. So this tilting is predominantly more, or what I can say here is it is play most vital role in case of this jib and cotter joints where the rods are square sections. If the rod is of square cross section, then it is going to be important. So as long as the rods are in a cylindrical sections, it is not going to be that much what you can say influence on the bending, whatever may be the bending stress which is induced in the parts is not that much influenced one. So then what you do is whenever there is a square type of rods, then in that case only you need to go for this jib and cotter joints. So that's why in the previous two joints, whatever we discussed, that is sleeve and cotter joint, socket and spygard joints. In those two joints, you have rods made of circular cross section only. Rods made of circular cross section. So that is we are taking. That's why we are taking the dimensions as D, D1, and D2, something like that. We are taking. So they are of having circular cross section. So as long as the cross section is circular, so the bending is not the bending stress is not that much influential in case of these cotter joints. Whenever there is a square rods are there, then you need to use the jib in order to eliminate that bending stress. So now we'll see this is the purpose of providing the jib in the cotter joint, and we'll see the design of this jib and cotter joint also. So now this is a figure which shows you a cotter joint with both jib and cotter. So here there is only one jib because the tapering is provided only on one side of the cotter. So in the figure you can clearly see that the tapering is there only on this side. So that's why the jib is provided only this side. So this side it is a straight edge. So you can see it is a straight one. There is no tapering, so no need to provide any jib for this side. So clearly you can see that the rod is in contact with this one. There is no clearance here. So that means the bending cannot be happened this side or tilting cannot be happened this side. Suppose if I don't have this jib here, so then your rod end is something like here, it is a square one. So then there is a clearance between this cotter and this rod end. So because of that clearance, it is going to tilt. So to avoid that tilting, we need to provide jib. Okay. So this is the picture which shows you your jib and cotter joint. So I think those who are having data book with you, just open your data book. Whether this is there in our data book or not, I want to know that. So in the older version, he has not given this thing in the data book. So Sai Krishna, now man, class lo or roll number 4, LE4, not a regular 4. These people have data book, I think. Maybe. Roll number 20, do you have a data book with you?
Sir, yes, sir, I am having, sir.
Hard copy or soft copy?
హార్డ్ కాపీ సార్, బుక్ ఉంది సార్.
Okay, then you see whether this is there in the data book or not.
లేదు సార్, నకిల్ జాయింట్ ఇచ్చాడు సార్ తర్వాత.
Only he has given only one joint, right?
ఎస్ సార్, స్లీవ్ అండ్ కాటర్ తర్వాత నకిల్ జాయింట్ ఇచ్చాడు సార్.
Okay, so you don't have the zip and cotter joint in the data book, right?
నో సార్, లేదు సార్.
Okay, so maybe in the new version also it is not available. Okay, so then what you have to do is we have to remember these relations. Suppose this problem comes in the examination, then what you have to do is you cannot rely on the data book because this is not available in your data book. So you have to clearly follow the procedure what we follow in case of the previous two giants. Here also will follow the same thing only. So you need to remember those things. So there are some empirical relations also there in this giant. You need to remember those things also. Okay, right. So now we'll go forward. So in this now, again in this there are four components. One thing what we call it as a rod, which is having a square cross section. So that's why it is called square rod. So this blue color, which is hatched in blue color, we'll call it as a square rod. Then this one we will call it as a strap, which is hatched in a pink color. So here you can see this is a strap, that is the second part. Rod is the first part, strap is the second part. Then you have a cotter, which is third one, and you have a jib, that is the fourth one. You have only four components or four elements in this one. So this is the front view and this is the side view what he has given. See, from the side view you can clearly see that. So this is going to be your rod, which is having square cross section. If I cut the rod here, this is going to be a square cross section, and he has taken the dimensions of that rod as x. So that means if this is x, this is also going to be x. So because it is a square in cross section, if this is x, from this diagram itself you can see that your b1, but b1 is nothing but the width of this strap. So that is also equal to x. So that means both the width of the square rod and strap is same, which is x only. So even though it is taken as b1, your b1 should be equal to only x, provided your rod is a square rod. So we will see what are various dimensions you need to calculate. So for rod you have to calculate what is x. So once you have x, this is also x. So you know those two dimensions. Then for sleeve you have to calculate what is b1, and also here you have these two dimensions. That is, so he has taken this one as a thickness of the sleeve. So now onwards they are not diameters. Why? Because they are in a circle. They are not a circular cross section. They are not having a circular cross section. So therefore this is the thickness of the strap you need to calculate. This is T1. So either side it is uniform. Thickness is same. This side is also T1 only. So you have to calculate T1 for the strap. And then once you have T1 and B1, so then the strap dimensions are over. So then for rod is over. For cotter again the same thing we need to use. So but here we'll call this the total width, that is the width at the center or at the center line of the joint. So this total width we'll call it as the mean width of jib and cotter. Combining jib and cotter will take the width, that is capital B. And this capital B is determined based on again the shear failure of this cotter, shear failure of both jib and cotter in combination. So once you have this one, then we'll take B is the width of the cotter and B1 is the width of the jib. So we'll use empirical relations to find out this B and B1 in terms of this B, capital B. So that means, so like what we discussed in the earlier case, there may be single jib or double two jibs. So when the two jibs are there, you have one empirical relation for B1. When there is only one jib, there is another empirical relation for B1 in terms of this B. So then we can calculate those dimensions. Then similarly, thickness of the jib also, we can use the empirical relation in terms of this B1 only. We can use this thickness of the jib. So like I can calculate the remaining parameters also. This is here, you can take what is the L2 value, that is height of the jib. This portion, that is we'll call it as T2 value. And then this L2 is nothing but again this is a jib dimension only. So these are all empirical relations only. Don't need to use any failure criteria for finding out these values L2 and L4. And similarly this L1 means, okay, here we need to use this one is the shear failure as the shear failure of the rod we need to consider as a failure to find out this L1, and similarly this LD, this is again empirical relation only. So here also you have one more thing, that is the sleeve end here. So here also you need to consider this distance. So what is the given the distance? The distance is calculated. So from this point to this point. So that distance is taken it as L2. This L2 is also determined based on the shear failure of the strap end. So you have to consider the shear failure of the strap end. So using that you can get this L2 value. So now we'll see one by one. So first thing, in case of the jib and cotter joint, what you need to do is you have to calculate what is X first. So you have to calculate X first, then we'll move on to the remaining dimensions one by one. So then for that, these are the various notations. Just now we discussed. P is the load carried by the rods. Then X is each side of the rod. B is the total width of the jib and cotter. That means combining small b plus b1 is your capital B. So small b is the width of the cotter and b1 is the width of the jib. Then capital B1 is the width of the strap. We have taken this one is equal to only your X only. T1 is thickness of the strap. T is the thickness of the cotter. Then these are the three permissible stresses in the rod, cotter and okay, if you use jib. So these are the three permissible stress values we need to consider for finding out the allowable stress value. Sigma T is the permissible tensile stress, tau is the permissible shear stress, and sigma C is the permissible crushing or bearing stress. Okay, so now we'll find out, first we'll find out what is X. So that X can be found out based on the tensile failure of this rod. Based on the tensile failure of the rod, you can find out this one. Since it is a square cross section, the rod is a square cross section of dimensions X by X, the area of this rod is nothing but X square only. So because X into X, it is a square cross section. So having side X, the area is X square. X square multiplied by sigma T will give you the tensile strength of the rod. It should be equal to your applied load P. So from this equation, if you solve this equation, you will get the X value. Once you got the X value, so your B1 is equal to X only. That is the width of the strap is same as the width of the rod. So you can calculate B1 also. Once you got the B1 values, then for the T1 value, we'll use the empirical relations. So these are the things I'll show it here. So anyway, this we already discussed. Tearing strength of the rod is nothing but X square into sigma T. So then if you equate that one to the applied load, P, you will get P is equal to X square into sigma T. From that you will get X value. So from this equation, the side of the square at X is determined. Then the other dimensions are fixed under. So now these dimensions are fixed. So you have to use only these empirical relations. Since these are not there in the data book, what you have to do is you need to remember these things. So without that, you cannot solve this problem. Okay, so you have to remember it. There is no other way for that. So B1 is nothing but, like I already told, B1 is equal to X only. Then T is the thickness of the cotter. So earlier we are taking the T is D2 by 4, but you don't have D2 here now. So we have B1 here now. So B1 by 4 you have to take. You have to take thickness of the cotter is B1 by 4. Then thickness of the jib, it is taken as thickness of the cotter. Both will be same. This is having both the cotter and the jib thickness is same. That is only T, which is equal to B1 by 4. Then height and length of the jib head. So like I said, T2 and L4, these are also empirical relations only. So T2 and L4 is also taken as thickness of the cotter. That is equal to T only. So now you need to remember these are the empirical relations. So only thing is, using failure criteria, we'll find out the X value. Once you got the X value, so your B1 is nothing but X only. Then T is going to be B1 by 4. Both the thickness of cotter and jib is same. So that is, we'll take it as T only, B1 by 4. Then height and length of the jib head. So you have to calculate. So that is also equal to T. So you have to remember these parameters. So then, now we need to compute what is the capital B, that is mean width of jib and cotter combined. So for that we need to use the shear failure of jib and cotter. So here this is going to be the shearing area. If I combine, earlier if you have only one cotter, here you have a small b here. So now we have both jib and cotter. So by combining width of jib and cotter, we are taking it as capital B. Therefore, your shearing area is nothing but 2 into B into T. If we multiply by the shearing area by allowable shear stress tau, you will get the shear strength, which is nothing but 2BT into tau, and you need to equate this one to P. So from that, you will get your B value. If you solve this equation, you will get the combined width of jib and cotter as B. You will get the B value from this equation. Once you got this B value, then there is a empirical relation between this B and small b and small b1, where small b is the width of the cotter and b1 is the width of the jib. So these are the empirical relations. Width of the jib is b1 is taken as 0.55 capital B, and width of the cotter is 0.45. So if you add these two, you should get a B. B1 plus B should be equal to your capital B. So you'll get it. So in case of two jibs are used, that means if there is a situation where two jibs are used, in that case each jib width is 0.3 B, then cotter width is going to be 0.4 B. So you have to take like this. So again, you need to remember, so only using shear failure of the cotter and jib and cotter as a criteria, we'll get the total width of jib and cotter. Then using these empirical relations, we'll find out what is the width of the cotter and what is the width of the jib. So once you've done that, yes.
So previous side లో H కి సంబంధించి empirical relations ఉన్నాయి కదా సార్, ఒకసారి అది పెడతారు సార్, నోట్ చేసుకుంటారు.
For X there is no empirical relation. So only X you have to calculate based on the failure criteria. That is tensile failure of the rod. You have to calculate X. Once you got the X value, then B1 is equal to X. From the diagram you can see clearly see that B1 is equal to X only. Then these are the empirical relations you have to take. So these are the corresponding to thickness of the cotter and jib and height and length of the jib head. So those are all are equal to only T. Yeah, note it down.
Yes sir, noted sir. Thank you sir.
Okay, right. So now, okay, so these are the empirical relations to find out individually what is the width of the jib and what is the width of the cotter when there is only one jib or there are two jibs. So then after this you need to find out a failure of the strap end in tension at the location of jib and cotter. So that means across the slot you need to find out what is the failure of the strap. So from that what you are going to get is the thickness of the strap you will get. So since here the strap is going to be something like this, so you can see that strap is okay. You can see the diagram here. The strap will be like this. Here you have holes here. So this is what he has taken it as thickness T1. This is T1. So now it is subjected to force here, this side P, this side P only. So now here you have to find out what is this T1. So for that across the slot you need to find out what is the resisting strength of this strap across the slot. So for that here, so what you can do is first if I take this area here across this area, that is width of the strap. So if I take the other view, that means 3-dimensional view, if I draw it, it is going to look like something like this. Here this dimension is going to be B. So if we extend this, here it is going to be have a hole here also, something like this. So now the area should be B into T1. B into T1 is going to be the total area. So in that I need to subtract the rectangular hole what we are providing for the, so entire hole, the hole is not there for the entire thing. So only you have a hole, something like this. Here this hole width, this is going to be the thickness of the cotter T. So this dimension is T1. So this is there. T1 into T is going to be the this is one side. So we have other side also same thing. Similar thing is here. So that's why you need to multiply this one by 2. So then this is going to be the area which is resisting the failure. Then if you multiply that one by sigma t, you will get the resisting strength. Then that should be equal to your applied load. So if you equate this one to P, you will get your dimension B1. So once you got the B1, then you got the all the dimensions for that strap. So then failure of scrap or jib in crushing. Actually, using this, just will check whether the crushing stress is within the allowable limits or not. So we'll check only that. We are not going to determine any dimension here. So then in that case, crushing area is going to be T1 into T. So that is the area which is in contact with the jib. So it is on two sides. So you have to multiply by 2. So then that multiplied by sigma c will give you the what is it, strength which is resisting this crushing failure. So then it should be equal to P. So from that, so we already calculated T1 and T will compute sigma c value from this. So then once you got the sigma c value, then you need to check the sigma c against the allowable sigma c value. So now if the sigma c is less than the allowable sigma c, then your design is safe. Otherwise you need to modify this dimension T1. Of course, we are not going to modify T value. We have to modify only T1 based on this equation. So that means we'll fix here T here. So here in place of sigma c, we'll substitute what is the allowable crushing stress. So then here the load is given to you P. So if you solve that equation, again you will get a new dimension for this T1. So that dimension T1 will give you the safe condition for crushing stress also. Okay, right. So this is the fourth point. What we need to do is then failure of rod end in shearing. So that means to calculate what is the distance, minimum distance you need to provide for the rod end. So that can be calculated further based on the failure of rod end. So here that length is we are taking it as L1. So 2 into L1 into X is going to be the area which is resisting this failure. So if you go back, if I go back to the diagram, so here you can see this is the rod end here. The distance here it is going to be L1 only. So here you have to take L1. So L1 into what is the width of this cotter? It is going to be X only. And this is failing. Why I am taking 2 here? Since this is failing double shear. So that's why I need to consider it as 2 here. It is going to fail in double shear. So that's why you need to consider it as 2 times. L1 into X is the single shear area. So since it is in double shear, you need to multiply by 2. Then this 2L1 into X is multiplied by tau will give you the resisting strength. Then it should be, if you equate this one to applied force P, from that you will get the L1 value. So that is the minimum length you need to provide for the rod end. So from this equation, the dimension L1 may be determined. Similarly, you need to calculate what is L2 also. So that is calculated based on shear failure of strap end. If you consider shearing failure of strap end, you will get the L2 dimension. So for that, again you need to consider what is the area. So why I have to take here 2L2 into 2. Again, I'll go back to that figure. I'll show it to you. Why you need to consider yes. So this is the figure. This is the your L2. So strap end. So from the cotter hole to the end of the strap, we'll call it as distance from the strap end required, minimum distance. So this distance he has taken it as L2. So from here to here it is L2. So now here we are not again here also it is, these two are also double shear because your thickness of the strap is B1, which is more than the thickness of this jib. So the thickness of jib is only this one. So that means the shearing will take place across this line as well as across this line. So this why, so only this much portion of this portion and this portion is coming out because of shearing. So this side and this side, that's why it is double shear. then I need to consider what is this area plus this area. So this area is same as this area, this one and this one is same. So therefore, that's what I'll do is I'll calculate this area and I'll multiply by this one by 2. So what is this area now? This area is nothing but here. This dimension it is T1. And what is the length here? Length is L2. So L2 into T1. L2 into T1 is the shear area if it is a single shear. If it is, then here in case it is double shear, you have to take 2 into L2 into T1, 2 into L2 into T1, and since you have one more area here, again you need to multiply this one also. That is 2 into L2 into T1. That's what I written here in the slide. So if I go back to the slide, yes, 2L2 into T1 multiplied by 2. So this 2 is for the double shear, and you have 2 strap ends are there. So for that you have to multiply that again by 2. So then you will get the total resisting area of failure. So then if you multiply this resisting area by allowable shear stress, you will get the resisting strength of that strap ends. So then you need to equate this one to P. So from this equation, if you equate that, you will get an equation, equilibrium equation. From this equilibrium equation, you can find out what is L2 value. Right. So with this, I think we already estimated all the values. Then the remaining values, whatever may be the length L3. So that is length L3 of strap end is proportional to the 2/3 of side of the rod. Side of the rod is we are taking it as X. The clearance is usually kept at 3 mm. The length of the cutter is generally taken as 4 times the side of the rod. So just like in the previous cases also, we are taken 4D. Length of the cutter we are taken as 4D. Now we are taken as, instead of D, now we have X here, so we have to take it as 4X. So this is how you can design a cotter joint with jib and cotter. And also here the supporting rod, the load is supported by square rods, not a circular rods. They are square rods. Generally whenever there are square rods, then only we will provide the jib. If the rods are circular rods, we won't go for the jib and cotter joint. We will go for either sleeve and cotter joint or maybe socket and spigot joint. Right? So I think it is clear to you, or if you have any doubt, then you can ask it. So if you don't have any doubt, then what you have to do is, I'll give you one problem to you, then you need to solve that problem. If you have any doubt, or if you want to note it down something, because these things are not available in your data book, we need to note it down, those reciprocal relations. If you want, I'll put those slides to you, just note it down, then you need to solve the problem. Based on these empirical relations, you need to solve this problem also. Based on all these relations, you need to solve this problem also. Okay? So, I think nobody is...
For 50 slide చూపించు. దీని ముందు స్టెప్ సార్. L1.
Okay. Okay, you note it down. Those are total six steps of calculation. So first you have to calculate X. Then once you got the X, you can calculate B1. B1 is nothing but your X. So then thickness of the cutter is taken as X by 4 or B1 by 4. X by 4 or B1 by 4. Both are same only. Then height and length of the jib head. If you want to take jib head, so that will take it as T only. So that is already calculated. So that is the first step. In second step, what you have to do is you have to calculate what is B. That is mean width of the jib and cutter. Then after that, you need to use again the empirical relations to find out what is the small b and small b1. So then the third step what we did is we calculated what is T1. T1 is nothing but the thickness of the strap. So that you can calculate it based on by considering the tensile failure across the slot for the strap. So you get T1. Then once you get the T1, then L1 and L2. Okay, I think I'll take you to the next problem, and then you try to solve that one. This is the sixth one. So there are 6 steps in this. Using those things, you can easily find the solution. Okay, I'm not going to show you the solution here. Just you note down this problem and try to solve this problem using those empirical relations, and then upload in the classroom for the attendance. If you have any doubt, then you can ask it. So ask now. We'll discuss your doubts also. The problem is, design a jib and cotter giant to carry a maximum load of 35 kilonewtons. P is given as 35 kilonewtons. Assuming that jib, cotter and rod are of same material and having following allowable stresses: sigma T 20 MPa, tau 15 MPa, and sigma C is 50 MPa. So now try to solve that problem and upload in the classroom. So we have 5 minutes time. So maybe after 5 minutes, for the next 15 minutes only the next class will start. So within that 20 minutes, it won't take 20 minutes also. It will take maximum of 5 to 6 minutes only. You can solve that problem and then you can upload in the classroom. Okay, so I am closing the class. Just to solve it and upload in the classroom.